All right, let's talk about understanding z-tables. So first we need to talk about the normal distribution. Just as a refresher, this is a specific pattern that shows up everywhere in statistics, right? Imagine you measure the heights of 1,000 people. You'd find that most people cluster around the middle height. Some people are taller, some people are shorter, but the differences aren't random. So there's a pattern, and when you graph it, you get a bell curve. Lots of people in the middle, less and less as you move towards the extremes. So that bell curve is called the normal distribution, also the Gaussian distribution. It's a mathematical shape. It's incredibly common. Test scores often follow it, heights follow it, weights follow it, IQs follow it. So here's what matters. All normal distributions have the same shape. They're all bell curves, but they can have different centers and different spreads. So, of course, the center is the mean. That's the average. The spread is measured by the standard deviation. Standard deviation tells you how far apart the data points are from the average on average. So this is important because it means you can't just compare raw scores from different distributions. You know, a score of 80 might be good in one distribution, terrible in another, depending on the mean and the standard deviation. And that is, of course, where z-scores come in. So they solve the problem of comparing things that are on different scales. A z-score is a way of converting any score so that it sits on a common scale. And the scale is called the standard normal distribution. So it's a normal distribution that's standardized so that the mean equals 0 and the standard deviation is 1, and every z-score is measured the same way. It tells you how many standard deviations away from the mean you are, right? Okay, so the formula, of course, is z equals x, the score, minus mu divided by sigma. So the score minus the mean divided by the standard deviation. All right, so okay, let's talk about understanding the z-table, right? Okay, so let me show you the table you have here, right? So this table is organized in a specific way, and I want you to understand exactly what each column means because I know some of you guys are struggling with this. So look at your table, right, and you see three main columns repeated twice, right? So the first column is Z. This lists the z-scores from 0 all the way to, well, on this page, it only lists it to 0.59. No, wait, we have multiple pages, yeah. So it lists it all the way up to 4.5, okay? So these are the z-scores you're going to look up. The second column is labeled percentage, okay? Second and third column is the percentage, but the second column is the percent to z. So this is the percentage of the distribution that falls between the mean, so z equals 0, and the z-score you're looking at. It's not cumulative, it's just the area in that specific band. The third column is percent in tail. So this is the percentage of the distribution that falls beyond or above the z-score that you're looking at. It's the area in the right tail. Okay, this is important. Your table does not give you cumulative probability the way some other tables do. Instead, it gives you two pieces of information for each z-score, and then you could calculate cumulative if you want. How much is between the mean and that score, and how much is the tail beyond that score. If you add those together, then you have half of the entire distribution, okay? And then if you multiply that by 2, you'd have 100%. Okay, so a z of score, which is exactly at the mean, so there's 0% between the z-score and the mean. And then 50% of the distribution is between the z-score and the tail. Okay, so if the mean is the z-score, if the z-score is 0, then half of the distribution is between the mean and the tail. The other half is below it. So you can see that if you add these two up, you're always going to hit 50% because that's half of the distribution. Then you multiply that by 2, you get 100%, okay? So let me show you exactly how to look something up. You have a z-score of, let's say, 1.23. All right, so right here, 1.23. I'm going to pull it down a little so we can see the charts up there. So 1.23 is the z-score, okay? Look at the second column. It says percent to mean, okay? So let's say that the value is, 39.07, Okay, so that means that 39.07% of the distribution falls between the mean of 0 and the z-score 1.23. And then if you look at the third column for the same row, 10.93% of the distribution falls beyond that z-score. So in other words, 10.93% of people have a z-score higher than 1.23. And let's see, what was it? 39.07% of people have a z-score between the mean and the z-score that you calculated. Okay, and add those two together, it equals 50%. And then, times that by 2, and then you would have the entire 100% of the distribution. Okay, so that's the key insight, right? So let me do a negative z-score example because they work the same way. The z-score is, let's say it's the same one, negative 1.23. It's going to be the same thing. It would just be in the opposite direction. Okay, it doesn't matter if it's positive or negative. The percentages are going to be the same for either one. The percent between the mean and z is still going to be 39.07. And the amount of people beyond your z-score is still going to be 10.93, whether it's on the negative side or the positive side. The table doesn't distinguish between positive and negative scores in terms of percentages. The percentages are the same. The only thing that changes is which side of the mean that you're on. Okay, so let's look at a few questions just to make sure that you guys understand this. So let's say the z equals 1.5. So what you do is you look for z of 1.5. Okay, we found that. So how many scores fall between average and z? Okay, between the mean and z of 1.5. That would be 43.32% of people or scores fall between average and your z-score. How many people or scores are above your z? Well, let's go back to 1.5. That would be 6.68% of people are above your z-score, or 6.68. I keep saying people, but scores are above your z-score. So let's say the question is, what proportion of all scores in the entire distribution are below your z-score of 1.5? Okay, so the proportion below the mean, okay, so 1.5 is right here, okay, everything below the mean, that's 50% of all the scores right there, okay. Then we need to add the amount of scores between the mean and your z, which was 43.32%. Okay, so the proportion of all of the distribution that's below 1.5 is 50%, everything below the mean, plus 43.32%, everything between the mean and 1.5 and the z of 1.5. Add those together, that's 93.32% of the entire distribution falls below that z-score. Okay, so let me say it again because it's important. To find the proportion below a positive z-score, you add 50% to the percent mean to z value. Okay. And if the z-score is negative, you just do it in reverse. So if we have negative 1.5, then 50% of all scores would be above the mean, plus the percent of mean to z is still 43.32%. Okay, it's the same exact thing, just on the other side. Let's say, ask what proportion of scores are above a certain z-score. So that's easy. Let's stick with our z-score of 1.5. The percent in the tail column is all you need for this one, okay? So here's your z-score. We don't need percent of mean to z. We need percent in the tail because that's everything that's above the z-score. So 1.5, 6.68% of scores are above your z-score. Okay, easy. And if it's negative, you just reverse it. It's very simple. Okay. So let's do another question of what proportion of scores fall between two z-scores. Okay, let's make it really complicated. So you need two table values for this now. So let's say you want the proportion between z of 0 and a z of 1.5. I mean, that's going to be, the z of 1.5, the percent to mean we're still on this page, so let's start with that, is 43.32%. Okay. And then that's your answer directly because the mean is 0. So 43.32% fall between 0 and 1.5. So let's make it a little complicated. What about between a z of 0.5 and a z of 1.5? Okay, so we know if we go up to 0.5, let's find not 0.05, 0.5, okay? All right, so we want to know how many are between 0.5 and 1.5. So between the mean and 0.5 is 19.15% of all scores. Okay, and between the mean to z, if you remember, between a mean and a z of 1.5, the mean to z was 43.32. Okay. So the proportion between them would just be 43.32 minus the 19.15. That's 24.17%. Okay, because the percent mean to z values are cumulative within the upper half, right? Everything from 0 to 0.5 is 19.15%, and everything from 0 to 1.5 is 43.32%. So the difference is what falls between 0.5 and 1.5. Okay. Let's do another one just to make sure that you get it. What about a z of -1 and a z of +1? Okay, now we're getting complicated. So let's find 1, and it'll be the same now whether it's negative or positive. Okay, so there's 1. I'll just put it here so we can use these down here. Okay, so a z of 1, the percent of mean to z, right? So if we're going from average to z for +1 is 34.13%. Okay, and then obviously the z of mean to -1 is the same, 34.13%. Okay, by symmetry, you know, there's 34.13% between 0 and 1 on the right, 34.13% between -0 and -1 on the left. So then you just add those together. 34.13 plus 34.13 equals 68.26. Okay, and of course that's the famous result from, you know, the empirical rule of 68% of any normal distribution falls within one standard deviation of the mean. Okay. So let me walk you through a complete problem so you can see all the pieces together. So the problem says, let's say, test scores are normally distributed, okay, with a mean of 500 and a standard deviation of 100. Actually, let me go get my iPad so I can write this down for you guys. Okay, so the problem is test scores are normally distributed, okay, with a mean of 500. So we'll draw out a normal distribution. Okay, the mean is 500, okay, and a standard deviation of 100. Okay, so what is the probability that a randomly selected student scored between 400 and 600? Okay, probability of 400 to 600. Okay. So the first one is you have to convert your scores to z-scores. We can't use a z-table without having z-scores. So for 400, the z equals the score, right, of 400 minus the mu, the average, which is we know is 500, divided by the standard deviation, which is 100. Okay, so that is -100 divided by 100, which the z equals -1. Okay, easy. Now for 600, okay, so what is the z for 600? So we have our score of 600 minus the mu, the average, of 500, divided by the standard deviation, which is 100. So you can probably see where this is going already. I made it easy. 100 divided by 100, the z-score is +1. Okay. So again, this is going to be similar to the last problem, where if we look up the z-score of 1, it's 34.13. So we have a score of 400, score of 600. You have 34.13% of people between 400 and 500, 34.13% of people between 500 and 600. You just add those together, you have 68.26%. Okay? Really simple. And so it doesn't matter what the z-score is. Let's say you've got a z-score of, let me just pick some random numbers, of 0.60. Okay, so this would be a z-score of 1 here, z-score of -1, and a z-score of negative, I don't know, 1.38. So you just look up the z-score of, what did we have, 0.60, and find the percent to mean. So that's 22.57% of all scores fall there, and then 1.38, 41.62%. fall there, and then you just add them together, okay? And whatever that equals, I'm not even going to bother doing the math, but whatever that equals is the cumulative percentage. Okay, it's very simple. Let's do one more example with. Okay, let's just do another few simple ones. You know, what proportion of scores fall below a certain score? Okay, you've got your standard distribution, you've got your average. We'll just pick a random score, z-score of 1.98. So this is 1, this is 2, so we've got 1.98 there. Okay, so how many scores are below that z-score of 1.98? And we're not just talking about average, right? We're talking about everything below. Well, we automatically know that there's 50% down here. Okay, so we already have 50%. Now all we need to figure out is what is between the mean and the z-score. So easy, so 1.98, where are we at with that? Okay, 1.98, we do the percent mean to z. So 61% of people are between the mean to the z-score. So then we just add 50% plus 47.61%, and then you have, what is that, 97.61% of all scores are underneath that z-score. Okay, you seeing how easy this is? Let's just do another one of what proportion of scores are above a certain score. So we've got our normal distribution with average. We'll pick a random score, see how many are above it. Let's go with 3.5. Okay, so we've got 1 standard deviation, 2, 3, 4. So we're right in here with a z-score of 3.5. How many are above that? It's not going to be a lot, right? That's a really high standard deviation. So we don't care what's below it. We're wanting to know how many scores are above that. How many scored higher? What percentage of scores are higher than 3.5? So very easy. We look up 3.5 right here, okay? And the first column is percent of mean to z. The second is percent in the tail. That's above the z. So there are, you don't have to do any math, 0.02% of all scores fall below 3.5. That's extremely rare, okay? So yeah, so I think we added it all up, did we not? I mean, I think I think that's all possibilities of what we can do. So this helps us to answer probability questions. Before z-tables and the normal distribution were understood, you couldn't do this. You had no way to say what proportion of people score above this or below this, or between two scores, but now you can using just a table and simple arithmetic. It also lets you compare things that seem incomparable. So like one test has a mean of 70 and a standard deviation of 5, the other has a mean of 500 and a standard deviation of 100. A score of 75 on the first test and a score of 600 on the second test look completely different, but convert both to z-scores, and now you can compare the two, okay? So the z-table is sort of like the bridge between abstract scores and real life concrete probabilities. And you can calculate your z-score, look it up, and suddenly you know where you stand in the distribution. You know what proportion scored better, what proportion scored worse, and where, the bulk of the data falls, or what's rare, how, or whatever you want to know, you can look it up. So that's the whole thing. Master the z-score formula, know how to read your table, understand what the columns mean, practice going back and forth between percent mean to z and cumulative probability, and do that, and you're good to go. All right, let me know if you have any questions.